Okay, as another option, we saw that we could leave behind one p orbital. So notice here in the topic of generating sp2 hybrid orbitals that we can only use 2 orbitals and leave one p orbital untouched. So the pz orbital is not shown, and we're not going to hybridize it. So we're going to put together one s orbital and 2 p orbitals. So 3 orbitals are going to go into the hybridization, 3 hybrid atomic orbitals should come out. So 3 hybrid orbitals have to come out. And these are going to be sp2. Notice the 2 indicates how many p orbitals were used in the hybridization process. Okay, here the 3 are shown, and notice now that we've tried to respect their original orientation as inherited by the type of p orbital that was used in the process. So these are now in different orientations. The size of the lobes is still asymmetric within a hybrid orbital, so that is the positive phase is largely the dominant feature, and the negative phase lobe is smaller as a result of cancellation of wave characteristics of the negative phase of a p with the positive phase of the s. Okay, this hybridization model allows us to describe pi bonds primarily. Okay, so when you take the 3 sp2 hybrid orbitals and place them over top of the nucleus to show their orientation and relative size, here you see them. So the sp2 orbitals are shown with their purple lobe again. The negative lobes are not shown for clarity, but you might imagine, again, they're on the opposite side of the lobe of interest. Okay, so they would be in behind here. Notice in the diagram here, we've also shown the unused pz orbital with its positive and negative phases shown this time. So this explains to us how we could show how a carbon might have a 120-degree bond angle in certain formats of a molecular system. sp2 hybridized carbon atoms are often seen in things like graphite, a major component of carbon fiber. So here 2 parts p and 1 part s have been used. They arrange themselves in a trigonal planar geometry, as you see with the purple lobes in our diagram here. Trigonal planar geometry, of course, is based on a 120-degree angle between the two. And this allows us to describe 3 sigma bonds in that trigonal plane, and the unused p orbital can be used to establish a pi bond. Okay, I'll just clean that up so you can pause the video if needed to read that more clearly. Very good. So now this pi bond, what does that look like? Well, that is a side-on overlap of atomic orbitals. So we saw if there's an unused p orbital that we could overlap that to establish a pi bond. So in carbon-carbon double bonds, we can explain the second bond of that carbon-carbon linkage with a pi bond. So that is, one of these bonds has resulted from an sp2 orbital overlapping with another sp2 orbital to give us a sigma bond. So this overlap between this carbon and this carbon has generated a sigma bond. And we have an unused p orbital with an electron available for sharing as well. Okay, so here we'll put these 2 electrons here. So we can get overlap between these 2 to give us positive constructive interference above the axis that joins the 2 carbon atoms together with their nucleus here at the box. And the negative phases can also constructively interfere to give us electron density below the axis, joining the two carbon centers together. So when we have electron density above and below the nodal plane on the internuclear axis, we know that we have a pi bond. So that explains the second pi bond down here. Because there's electron density both in the axis and above it, you can imagine this restricts the rotation of the units bonded. So pi bonds cannot rotate without breaking the pi bond. Other pi bonds can be generated by atomic orbitals that aren't hybridized. So in this case, a p with a p, like we shown here, or even a p with a d orbital in more complex molecular systems. Okay. So what does that look like when we try to show all of that together? If my diagram on the previous slide wasn't good enough, we can see here that there was an sp2 positive lobe here from one carbon center overlapped with another sp2 positive phase of another hybridized sp2 orbital there. That gave us the sigma bond listed here. And then because we had reserved a pz orbital with positive and negative phases here that was unhybridized, that we can expect constructive interference above and below the plane to give us half of the pi bond up there and the other half down below. Okay, so that gives us the carbon-carbon double bond, and we can also see here that additional sigma bonds have been generated on the other side of each carbon, here where the 1s orbital of the hydrogen has overlapped with a second sp2 hybrid orbital on that carbon, and likewise 120 degrees away from that. Okay, so the pi bond is half above and below the plane as we indicated, and we can consider that as being symmetric, and therefore if each line in a drawing of a bond represents two electrons, we can imagine essentially one electron above and one electron below that axis joining the two atoms. And we cannot have a pi bond between two atoms without first having a sigma bond to give us the hybridization. So every double bond has a sigma bond and a pi bond. And together they restrict rotation. So rotation cannot occur. Okay, the last option is sp hybridization. This is a little less common for general materials in this course, but we'll cover it for completion. So here we'll only use one p orbital and leave the py and the pz orbitals for other bonding uses. So here two atomic orbitals go in, two hybridized atomic orbitals should come out of the hybridization process, and now we see their size and shape and orientation reflected in the diagrams here. And if we put them over top of a carbon and not show the negative lobes, you can see that the sp orbital is in one case here, and the other sp orbital is here, and their negative phase lobes are not shown. So these are two hybridized atomic orbitals ready to give us bonding that is 180 degrees away from each other. The unused py and pz orbitals are also superimposed on this diagram, and we see them with their negative phases listed. So one py orbital is here, there's the negative phase. The other unused pz orbital is here, positive phase there, and then the negative phase coming out of the page towards us. This allows us to describe linear geometries at the carbon where we have bonded atoms 180 degrees away from one another. We know that one part P and one part S went into the hybridization process, and this can help us explain how we form two sigma bonds and two pi bonds as a result. So a sigma bond at left, a sigma bond at right, 180 degrees away from one another, and how we could make pi bonds above and below the plane, as we'll see on the next slide. Here's the example of acetylene, a molecule that can be used to make polyacetylene, a conducting polymer, something that's like an organic metal, very interesting material. So at the carbon, we can see that we need to form a sigma bond. So one of these bonds here is a sigma bond, and so we can describe that as being the sp orbital with the negative phase orbital shown here, and that is going to overlap with the sp orbital, the neighboring carbon, with the negative phase shown there. And we have unused pi orbitals, so we could use one of them like we did for ethylene, this double bond case, above and below the plane. And we'd expect overlap here and here. And because we have an additional p orbital unused, shown that here and here, as I transfer our thoughts to the second diagram, you can see that we can get similar overlap forward on the page and behind the page when we think about the three-dimensional space about the axis joining the two carbon atoms together. Okay, so here's our sigma bond, sp overlap, and then we have from the py's up here in yellow is half of one pi bond. Down below here is the other half of that pi bond. That's our first pi bond. And then switching colors just to make it more clear, behind the page is the first half of the second pi bond. And then coming out of the page is the last half of that final pi bond. So the triple bond has one sigma bond, one pi bond there, and a final pi bond there. So a triple bond has two pi bonds and one sigma bond. A triple bond consists of one sigma bond and two pi bonds. The pi bonds are perpendicular to one another, as you can see, so they are not allowed to occupy the same three-dimensional space about the axis of the two atoms. And triple bonds have a barrel-type electron density as a result, right? We have electron density above and below and in front and in back, almost like a barrel, like a pipe. And so, of course, bond rotation is going to be even more restricted because we have structure before, in front and back, on top and below, restricting that rotation.